Okay, so I hope you can see my slide. Can you see it?
Yes.
Yes, Doctor.
Okay, that's good. Okay, so as for today, we're going to discuss on chemical bonding. So in in our daily life, let's say human to human, we have uh, sometimes we call it let's do some bonding, or for married couple people. So there is a bonding, the marrying bonding. But then how about in element? How can we describe the bonding that happen to the element? So that should be on the chemical bonding point of view. So in this chapter, we will discuss on valence electron and Lewis structure, the ionic and covalent bonding, resonance, hybridization of atomic orbital and intermolecular forces, and metallic bonding. As introduction, the attractive force that hold atoms together in compound are called chemical bonds. So that's how the element been bonded to another element. So either in the similar element or with the different element. So the electron involved in the bonding are usually those in the outermost shell or electron that been the further from the nucleus. The electron that located on the outermost or the shell valence. Okay, then if we draw the structure, so let's say we have nucleus and we have the orbital n equal to 1, n equal to 2, n equal to 3. So n equal to 1, n equal to 2, n equal to 3. So in n equal to 1, the maximum electron is 2, n equal to 2, maximum electron is 8, and n equal to 3 is also 8. But then, let's say we have one orbital that located at n equal to 3, or in this case, the outermost, the valence shell. So this type of electron that will be contributed to the reaction. So whether in this case it going to be either to be shared or to be donated to another element. So that's how the chemical bonding took place. And in chemical bonds, it is classified into two types. The first one is ionic bonding. This result from the electrostatic attraction among ions, which are formed by the transfer of one or more electrons from one atom to another. So to cut it short, ionic bonding must involving donating or transfer of electron. So one element need to be donate electron, one element need to accept the electron. That's how the transference of electron took place. That will be ionic bonding. Second chemical bonding is covalent bonding. This is resulting from the sharing one or more electron pair between two atoms. So each element have their orbital electron, and they uh, sorry, each element have the valence electron, and this valence electron will be shared together to make whether single bond, double bond, or triple bond. I do believe that you learn it in organic chemistry, where or how the bonding took place. There's the single, double, or triple bonding. The easiest way to draw the structure or how to represent the bonding that took place is through Lewis structure. So uh, this guy, or Gilbert Newton Lewis, that's why the Lewis structure came from the scientist Lewis, J.N. Lewis. The valence electron play a fundamental role in chemical bonding. The electron transfer lead to ionic bonding. The sharing of electron lead to covalent bonding. the electron are transferred or share, it's not off, this is supposed to be or, either transferred or share to give each atom a noble gas configuration, octet. So the main reason is to get the octet configuration, meaning that each electron need to have 8 electron, except for hydrogen. Hydrogen only can hold 2 electrons as the octet configuration. Other than that, it required 8. So it can be represented using Lewis symbols, where a chemical symbol represents the nucleus and the core electron. The dots around the symbol represent the valence electron. So let's say we have example of hydrogen. Okay, so Lewis dot or the Lewis symbol will represent hydrogen with 1 electron, since only 1 electron for hydrogen at the valence shell. So we have another example here, silicon. Silicon have 4 electron at the valence shell. Same goes to carbon. Carbon also have 4 electron at the valence shell. Okay, so this is how we represent the Lewis symbol. So other than that, we have, let's say, sodium. Sodium also have 1 electron at the valence shell. Okay, on ionic bonding, how it is formed. So in this bonding, an ion is an atom or group of atom possessing a net electrical charge. So we already discussed it previously. So where the ion can come in two basic type. The first one is positive ion or cation. So in this case, atom lost 1 or more electron. So for example, we have Na plus, Ca2 plus, Al3 plus. So it will be based on the valence electron on that element. Okay. The second one is negative ion or anion. To become an ion, this atom are gain 1 or more electron. So for example, chlorine ion. So chlorine have valence shell electron of 7. It can accepting 1 more electron. So that's why the charge of chlorine is -1. Okay, that's for fluorine example. For oxygen, it will be oxygen 2 minus to achieve octet of 8 electron. The ionic bonding are formed by attraction of cation for anion, usually to form solid. Commonly, metal react with non-metal to form ionic compound. So this is the rules, metal and non-metal. So the formation of sodium chloride is one example of an ionic compound. Okay, so let's take sodium chloride as an example. If we have the Lewis structure, Na will be drawn like this, Na with 1 electron on the valence shell. And let's take chlorine. Chlorine with 7 electron on the valence shell. Okay. We described just now, it need to be donate and accepting on ionic compound formation. So in this case, sodium tend to lose an electron to form sodium plus, in which this is the octet, 1 electron from the valence shell been eliminated. And for chlorine, it will accepting the electron from sodium to complete the octet of 8 electron. So chlorine will have negatively charged. Since both having uh, only one charge, meaning that sodium 1 plus and chlorine 1 minus, it is neutral. So as a result, we have sodium chloride. So sodium chloride is our table salt. We can find it in our kitchen, and it is in solid form. So that's an example of ionic compound. Okay. So we have another example for barium oxide. For barium, it has 2 electrons on the valence shell, and for oxygen, it has 6 electrons on the valence shell. So each of electron in barium will be donated to oxygen. And in this case, barium will be uh, will having 2 plus ion or barium 2 plus, and oxygen that already been accepting 2 electron from barium will be having oxygen 2 minus charge. Okay, since both are equal, then the final electronic or chemical configuration will be barium oxide. So in case of magnesium chloride, magnesium also have 2 electrons on the valence shell, and for chlorine, it will have 7 electrons on the valence shell, in which 1 electron from magnesium will be donated to individually one chlorine atom. In case of oxygen, it required 2 more electrons. So both electron in barium will be donated to oxygen. But in this case, for magnesium chloride case, if 1 electron given to one chlorine atom, it already achieving the octet. So 1 more electron need to have another atom. So that's why it required 2 atoms of chlorine to complete the octet of magnesium 2 plus. Okay. So in this case, we have magnesium 2 plus and 2 chlorine atom. Okay, since the charge is not equal, then finally we will have magnesium and chlorine MgCl2. Okay, next on covalent bonding. Covalent bonds are formed when atoms share an electron. So for ionic bond, it took place between metal and non-metal. For covalent bond, it will be non-metal with non-metal. Okay. So covalent bond typically occur in organic compound. So the element that reside on the right side of the periodic table. So typically that will be the non-metal compound. Okay. If the atom are share 2 electrons, a single covalent bond is formed. If the atom share 4 electrons, a double bond will be formed. If 6, then triple bond will be formed. The attraction between the electron is electrostatic in nature. So let's see how it took place. Okay. We have example of fluorine gas, F2. So each fluorine atom consists of 7 electrons on the valence shell. Okay, so to achieve a complete octet configuration, each fluorine required additional 1 electron. Right, this is the targeted or required. So how it can happen is by combining 1 electron from each fluorine and form uh, combination of or single bonding of fluorine and complete the octet. Okay, so we go to here, and then this will be the final form of single covalent bond from fluorine. So single covalent bond consists of 2 electrons. Okay, so we can say that 8 electrons already been achieved. So we can count it as 1, 2, 3, 4, 5, 6, 7, 8. Right? So each fluorine atom will have 8 electrons as the octet completion. Okay. So how about water molecule? In water, H2O, we have 2 hydrogen atoms and 1 oxygen. Okay. For hydrogen, it will have 1 electron on the valence shell, and for oxygen, it will have 6. So for oxygen, it required another 2 electrons to complete the octet, and for hydrogen, it can release, it need to release 1 electron to complete the octet. So the electron from both hydrogen uh, is not released; it need to be shared to complete the octet for case of covalent bonding. So it will be shared to oxygen. Okay. So this happened by the overlapping of orbital. So we have s orbital, p orbital, d orbital, right? As we discussed previously. So the electron will be overlap on the orbital and have the formation of bonds. So in this case, water will have HOH, uh, the final shape of water will be HOH. This is due to the lone pair electron that exists in oxygen that gives some repulsive to the hydrogen atom. But then we can represent it like this to show how the additional two single bond that happen on the between hydrogen and oxygen. Okay, that is for single bond. For double bond, two atoms share 2 pair of electron. So in case of carbon dioxide, okay, so in this case, I draw here. Okay, 6 electron in oxygen, and then for carbon we have 4 electron in the valence shell. What will happen is that 2 electron from each oxygen will share the electron with the carbon. So that at the end, we will have double bond formation in carbon dioxide. And for triple bond for nitrogen gas, so let's say we have nitrogen. Nitrogen have 5 electron on the valence shell. So actually we can also draw like this to make easier presentation of bonds that took place. So it will be shared, and finally we will have a triple bond of nitrogen gas. So if we calculate the electron each nitrogen will have 8 electron. So electron 1, 2, 3, 4, 5, 6, 7, and 8. So that is the reason why sharing of electron is required to complete the octet. So same goes for this is, let's say this is nitrogen 1 and we have nitrogen 2. Similar calculation can be made. 1, 2, 3, 4, 5, 6, 7, 8. Okay. We have another example of ammonia that consists of 1 nitrogen and 3 hydrogen. So let's say we have ammonia, nitrogen. In ammonia, we have we have 5 electron in valence shell. And for hydrogen, it will have one electron on the valence shell. Okay, so the sharing will be like this. Okay, so either you may write it using the Lewis structure like as this example, or you can draw it using the bond structure. It is similar. Okay, so in case of ammonium, so for this case, we call it as a covalent dative. So let's say we use the similar bond that already took place in ammonia. There will be additional 2 electron in nitrogen. So let's say in presence of H plus, what can happen is that 2 electron from nitrogen is not donated, is shared to one more proton or hydrogen plus here to form covalent dative formation. So we will have at the end NH4. So overall will be positively charged due to the presence of positive charge on the incoming hydrogen. Now, for covalent bond, how about the length? So let's say the general rule will be a triple bond will have a lesser or shorter length compared to the double bond and compared to single bond. In hydrogen gas, for example, the length between each nucleus will be 74 picometer, and for hydrogen iodide, Hi, the length will be 161 picometer. So for another example, to compare the single, double, and triple bond, single bond will have a length of 154 picometer, and then when it becoming, or in the case of double bond, the length is 133, and the triple bond will have bond of 120. So we can see that the length is decreasing. So what happened is that with the additional bond from single to double to triple, the attraction to the nucleus center will be greater. So each nucleus will be shrink and reduce the bond length. So same goes to the CN. CN single bond 143, CN double bond 136, and CN triple bond 116. So we can see that with the increase of bond from single to double to triple, the length will be decreased due to the attraction of nucleus. Okay. Next on the polarity. In organic chemistry, we always discuss on polarity. So polarity, how it's formed. The polar covalent bond or polar bond is a covalent bond with greater electron density around one of two atoms. So each either one of the atom required a greater electron density. So we have example of HF here. We consider that hydrogen will be the electron poor region since there is no additional electron in hydrogen bond. So we can put it as electron poor region. So electron poor region or delta positive. But in fluorine, fluorine have additional 6 electron. So we say it is rich of electron and put it as delta negative. So polarity meaning that uh, the density of electron will be greater in fluorine. So we can say that the polarity will go to the side of fluorine. Okay. So for example of carbon, CC. For ethane, for example, each carbon already have a bond with the hydrogen, and then both sides don't have either poor region or electron rich region. So this one is non-polar. But then for HF or any other example, this will be a polar molecule. Okay. But then let's say this is an example of ethane. So in case of additional of other element, so in this case, ethanol, there is electron rich region at oxygen, right? So this will be a polar molecule since the electron density already moving forward towards oxygen. It required an element that have the electron rich region to become a polar molecule. Now, on writing the Lewis formula, the octet rule state that representative element usually attain stable noble gas electron configuration in most of their compound, and Lewis dot formula are based on the octet rule. So we need to distinguish between bonding or shared electron and non-bonding or non-shared electron or lone pair of the electron. Okay, so there is a rule called as octet rule. So this is the formula, the rule formula, n minus a equal to s, NAS. N is the needed number of electron needed to achieve a noble gas or octet configuration. N usually have a value of 8 for all of the element, except N have a value of only 2 for hydrogen. Only hydrogen have the exceptional on the needed electron to achieve a noble gas configuration. A is the available, meaning that available electron on the valence shell. Okay, so A is equal to the periodic group number of each element. A is equal to 8 for noble gas. Okay, S the shared number of electron. So we can get it from N minus A. Then we get the shared electron. And other than that, we have A minus S. This will be the unshared electron or the lone pair. Okay, let's see how the equation work. Before that, for ion, we must adjust the number of electron available. This is only for ion in case of you are required to calculate or draw the structure of an ion. So we have one electron to the element or the atom for each negative charge, and subtract one electron for the element for positive charge. Okay. Next, the central atom of the molecule or polyatomic ion is determined by two factor. So let's say you are given a structure and you need to determine which will be the center atom, will be the outer atom. Okay, the atom that required a large number of electron to complete the octet will go to the center. So we will require, since we have n equal to s, minus a equal to s, a is the available, and from the available we can see which atom will be the center. But then for two atoms in the same period group, the less electronegative element goes to the center. And that if we have, for example, we have carbon, silicon, and so on, going up to the period will be more electronegative. So meaning that it will be the element that uh, downing the period. Okay, so let's take hydrogen cyanide. So how can you draw the Lewis structure formula, or dash formula to this molecule? Okay, we will calculate the n needed for complete the octet. So we have hydrogen. Hydrogen only required 2 electron. Carbon, it will require 8 electron. Nitrogen is 8. Total of that, we have 18 electron. The available, the available is the electron that possessed on the valence shell. For hydrogen is 1, carbon 4, nitrogen 5. Total of 10 electron. Since the formula is n minus a equal to s, then s will be 8. 18 minus 10, we have 8. This is share electron. For unshare is a minus s. 10 minus 8, we have 2 electron. So we have this idea, the rough idea to draw the Lewis dot structure. Okay, so in this case, carbon will require the largest number to complete the octet. Okay, for hydrogen, it only required 1 electron to complete the octet. Carbon required additional 4 to complete the octet. And nitrogen will require 3 electrons to complete the octet. So then we can say that carbon will be the center element. So in this case, we have carbon on the center element, and hydrogen and nitrogen will be the outer element. Okay, so here we have identified that 8 electron will be shared. Okay, or we can draw it like this too. 1, 2, 3, 4. Hydrogen, only 1 electron, and nitrogen, 5 electron. 1, 2, 3, 4, 5. Okay, the shared electron will be 8. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. So this will be the 8 electron that calculate from S. Then we have unshared, two electron only. So this will be 1 and 2. So these 2 electron will be the unshared electron. Okay, so either you can write it in the Lewis dot structure or using the bond structure, bond drawing. So both are acceptable. Okay, so let's look on the next example. Lewis dot and dash formula for sulfide ion SO3 2 minus. Okay, for sulfur it need 8 electron to complete the octet. For oxygen is also 8. So we have 3 atom of oxygen, we just multiply it by 3, total up of 32 electron. 24 from oxygen and additional 8 from sulfur. So we have 32. The available sulfur have only 8 electron on the valence shell. 6 electron on the valence shell. Same goes to oxygen, 8, right? So uh, 3 atom of oxygen, we have 18 here, plus 6 from sulfur. And remember the rule of ion, if there is negative ion, we need to add to the electron that available. So in this case, we have 2 electron, then we just put 2, 2 electron, additional 2 electron, total up of 26 electron. N minus A, we will have 6 electron, and A minus S, we have 20 electron. Thus, the sulfide ion has 6 electron for shared and 20 electron unshared electron. So which atom will be the central atom for this example? Since oxygen and sulfur will be in the same group, oxygen will be more electronegative compared to sulfur. So that's why sulfur will be the element in the center. Okay. So just now we have 6 shared, 20 unshared. Okay. So when you try to draw it, we will have, sorry, 6 shared electron. It came from here, 1, 2, 3, 4, 5, and 6. So this will be the shared electron. And then we have 20 unshared electron. So here 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 20 unshared electron. And don't forget we have charge. So we have 2 minus as a sulfide ion charge. Okay, that is how we calculate to draw the Lewis dot or dash structure for given molecule. And then we also can calculate the formal charge. Wait, So we can calculate the formal charge where the charge of the molecule, either positive or negative, be been calculated here. Okay. Okay, let's look how do we calculate the formal charge. Formal charge is the equation will be the number of valence electron minus number of lone pair electron minus half number of bond pair electron. Okay, so in this case, NO2. Okay, so the formal charge for that need to be calculated individually by atom. In case of oxygen atom, the valence electron for oxygen is 6, and the lone pair electron for oxygen is 4. So we have 1, 2, 3, 4, and minus half number of bond electron. So in this case, I make it bigger. So if we have 1, 2, 3, 4, half number of bond pair electron. So finally, we will have 6 minus 4 minus 2. Then the formal charge of oxygen is 0. Okay. And for nitrogen, nitrogen have 5 valence electron. And in this case, nitrogen doesn't have lone pair electron. And we need to minus half bond pair electron. So for nitrogen, we have 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen have 8 bond pair electron. So in this case, the formal charge for nitrogen is +1. Then we need to calculate the overall formal charge. So we have 2 times 0, meaning that 2 times formal charge of oxygen plus 1 formal charge of nitrogen. So in this case, 2 times 0 plus minus 1, plus 1 from nitrogen, and the overall formal charge will be +1. So in this case, nitrogen will be positively charged, or we can draw it like NO2 plus or plus. Okay. Okay, I think I will stop the class until this slide. Is there any question?